All right, where did I put that? Good grief. I can't find anything in here. I don't know. Oh, crap. Even though my training is in mathematics, I do have an interest in astronomy. And lately I've been interested in listening to all the newly discovered exoplanets that they have. And among these, a system that particularly caught my attention was the Trappist system. If you're not familiar with this, Trappist 1 is a system of exoplanets that are in orbit around a small red dwarf star. There are 7 planets, and several of these are in the habitable zone. And because it's a red dwarf and because they're so closely clustered around each other, you have the prospect of what I call a Star Trek sky there, where you can look up and see quite a few planets. And so what I've done is I've gathered together the data and I have figured out how the various skies would look. And I'd like to share the math of this and at least how one of the skies would look. Stick figure looking at a planetary body out in space. And I've drawn the line of sight here to it. And so what I want you to notice is that how big a planet looks against the sky is all about the angle theta that is subtended by the planet. And so I've set this diagram up with the assumption that we know two things. The distance away from us, the planet we're looking at, or the distance from us to the center of the planet, and then the radius of the planet. And then using that data, I'm going to take a very simple formula and do a calculation of how big an angle that should subtend. Okay, let's take that pretty picture that I drew of the observer and the planet and distill it down to its mathematical essence. What I have here, okay, is the important right triangle. This is the point where our observer is looking. This is where our observer is. This is where he's looking, and this is the center of the planet where he's looking. This point he's looking at is gives us a right angle with the radius of the planet. The distance from our observer to the center of the planet, not that he can see the center of the planet, is A. And the radius of the planet is R. And this represents 1/2 of the angle that the observer sees, or that is subtended by the planet. And this is theta over 2. And so simply by definition of sine, I have the sine of theta over 2 is equal to R divided by A. And so theta over 2 is equal to sine inverse of R over A. And so the angle theta is equal to 2 times sine inverse of R over A. And so this is it. This is an astonishingly simple formula. Okay, let me explain to you what I have in the data. The first column are the planets, and at this point they've been numbered B through H. I don't know why A was left out. The masses, this is put in terms of the masses of the Earth. And so planet B has a mass of 1.374 times the mass of the Earth. There is a margin of error, which I chose to leave out. The major axis is how far the center of the planet is from the center of the star. And this is in astronomical units. An astronomical unit is how far the Earth is from the sun. And so this is a fraction of this. And the radius, again, this is given in terms of Earth radii. And so in order to perform all of these calculations, I did the conversion to kilometers, okay, which is what the appropriate unit in this case. Okay, there are 7 planets whose skies we could look at. The one I've chosen to look at is planet F because it seemed to be the most Earth-like of all of these in terms of size and temperature. And so what I have here is I have each of the planets and how it would look when it's the biggest in the sky and how it would look when it's the smallest in the sky. And the units I've given these are in terms of radii of the moon. And so planet B is about has a diameter that's a little bit over a third of the moon's diameter, as is planet C, planet D. Planet G will be slightly bigger than the Earth's moon at its largest. Now, the interesting thing is that we can also see when it looks in its smallest, because these aren't orbiting planet F. They're orbiting the central sun, and so their distance from planet F will vary widely. And so if I take a look at planet G, while it is bigger than the moon at its closest, at its farthest, it's going to be about 1/10 of the size of the full moon. And we have a similar variation among all of these. This extreme variation happens here because planet F is relatively far out, and the farther out you are, the more variation there is going to be in the distance between you and each of your other planets on an annual basis. But here, annual only means a few days because these guys are being whipped around that little star because they are so close to it. Yeah, who is it? No, I'm not doing anything. Come on in.